Hello, and welcome to Lesson 8, Two-Sample Hypothesis Testing. This is part of the lecture series Applied Statistics Using Programming, brought to you from Sogang University. My name is Professor Ian. Let's get started in talking about two-sample hypothesis tests. So, two-sample hypothesis tests. Let's get started. The content for this lesson is two-sample hypothesis tests. Section 2 is comparing two means in an independent sample, and Section 3 is comparing two means using a paired sample. There are other two-sample tests not covered in this course, such as testing a proportion, comparing two variances, or looking at confidence intervals, are not covered in this course. What are two-sample tests? In the previous lesson, we learned about one-sample hypothesis tests. A one-sample test compares a sample estimate to a non-sample benchmark. That non-sample benchmark is usually an assumption about the population. Often a presumed average of the population is used in that hypothesis test. A two-sample test compares two sample estimates with each other. So in short, a two-sample test is using two different samples and testing whether those are coming from the same population or if they're from two different populations. Two-sample tests are especially useful because they possess a built-in point of comparison. In other words, we don't need to make an assumption or presume something about the population. In a two-sample test, we have two samples of data and we can directly compare them. The logic of two-sample tests is based on the fact that two samples drawn from the same population might yield different estimates of a parameter due to chance. If we have one population and we take a sample from that population, and then we take another sample from that population, those two samples will not be equal. Why? Because there's a lot of variation within individuals of a population. So to test whether the difference is due to just randomness, depending on who you selected for your sample, or whether the difference represents a real difference in those two groups, we can use a two-sample test to figure that out. Therefore, we are essentially testing whether the two samples are different due to randomness from the same population, or if the two samples come from two different populations. If the two sample statistics differ more than the amount attributable to chance, then we conclude that the samples come from populations with different parameter values. In other words, if there's a really big difference between the two samples, we would assume that that difference is probably not due to chance. If it's very big, probably it's more likely that that difference comes from those samples coming from different populations. Okay, let's take a moment just to talk about degrees of freedom in statistics. Degrees of freedom, usually annotated as DF, are the number of independent pieces of information needed in a calculation. So let's think about the example of a coin toss. If I have a coin and I flip a coin, the outcome is either heads or tails. In order to know the outcome, how much information do I need? Do I need to know the number of heads and the number of tails? Well, let's say the outcome is heads. In that case, how much information do I need? Do I need to know heads and tails? If I know that the outcome is heads, I already know that it's not tails. So I only need to know one piece of information. Let's take a similar case of 100 coin tosses. If I know the outcome of the number of heads or the total number of tails, how much information do I need? Again, if I know how many heads occurred in those 100 coin tosses, I already know how many tails there are because I can just subtract the number of heads from 100, the total. That would give me the number of tails. In other words, I only need one piece of information here. I only need to know how many heads there were in 100 coin tosses. Let's look at a slightly different example here. How about a traffic light? A traffic light, there are 3 different options. Let's say that you arrive at a traffic light and you want to tell me what color it is, but you can't say the color that it is. In other words, you could tell me that it's not red, and you could tell me that it's not yellow, and now automatically I know that it's green. So, in order to explain what color a traffic light is, we only need 2 degrees of freedom, and we know what color it is, even though there are 3 colors that it could be. There's 3 possibilities. The degrees of freedom are generally k minus 1 in most cases, not in all. So, for example, there are 2 possible outcomes, but we only need to know the outcome of one, and then we know the outcome of the other. The total number of heads also tells us the total number of tails. We can infer that information. With a traffic light, there are 3 possible outcomes. We only need to know 2 of those outcomes to know the 3rd outcome already. Let's define this a little bit more formally. So the degrees of freedom are the maximum number of logically independent values, which may vary in a data sample. So how does this work for calculating, let's say, an average? Let's say my sample average is 10. So I only have 3 observations in this example. One of those observations is 9. The second one is 10. So if I know my x bar value, the sample mean, then do we know the last value right here? Sure, if I know that the average of these 3 values is 10, then I can just pick the number that would make this average 10, which would be the number 11, right? If we know the sample mean, then how many values can vary? Again, we have k minus 1. So a sample mean looks like this. It is the values summed divided by the total number of values. That gives us our sample mean. To calculate S, the sample standard deviation, we need to know the difference between each value of x, and we make this adjustment on the bottom for the sample size. So, what is that adjustment? That is the degrees of freedom. In a 1-sample t-test, we need to know the mean of the sample. The degrees of freedom are n minus 1. But in a 2-sample test, we have 2 different samples. So when we have the means of 2 samples, the degrees of freedom are n minus 2. Let's look at the first example. In the 2-tailed test, I find it a little bit more intuitive to understand. So let's just look at the 2-tailed test for now. In a 2-tailed test, the null hypothesis is mu1, which means the population average that we got the first sample from minus the population average that we got the second sample from are equal to D0. In other words, the difference that we assume of that population. In most cases, in almost all cases, it's common to expect that difference is 0. In other words, we're expecting that there's no difference between the 2 groups. In that case, let's look at the second example on the bottom. For the common situation of testing for a 0 difference, meaning both samples are coming from the same population, or there's no difference between the populations, there would be a 0 difference in the 2 population means. Therefore, we can summarize as follows. mu1 minus mu2 equals 0, meaning there's no difference between the population that our first sample came from, and there's no difference from the population that our second sample came from. That would be the null hypothesis. However, if we have evidence to show that these 2 values are very different from each other, we might assume that the difference is not 0, meaning they're not equal. They're not coming from the same population. There are 3 cases to consider. So mathematically or statistically speaking, there are 3 ways to calculate this. The first case is the known variance case. When variances are known, use the normal distribution for the test. Okay, so this So in what circumstance would we know the variance of the population underlying that sample? Almost never. The second case is we don't know the variance, but we assume that they're equal. Since variances are unknown, they must be estimated and the t-distribution is used to test the means. If variances are equal, then S1 and S2 are used to estimate a common pooled variance. In other words, if our two samples are coming from populations with an equal standard deviation, if we know that those standard deviation, or we know that variance is equal, then we can simplify our calculation as follows. However, in what case should we assume that they're equal? I would argue we should never do that unless we fully know the situation, which is almost never in real research. So let's look at case 3. Case 3 means we do not know the variance and we assume the variance is unequal. Why? Because we have no information to tell us that they are equal. So in most instances, we should use case 3 because it makes the fewest assumptions about the population and the samples that we're using. Okay, so if population variances are known, we can use a normal distribution. If the population variances are unknown, then we're less sure about what they are, so we should use the student's t-distribution. What's the difference between the normal distribution and the t-distribution? It depends on the sample size. If the sample size is infinitely large, the normal distribution is equal to the t-distribution. However, if you have a very small sample size, the t-distribution is more uncertain. It has fatter tails in that distribution. So the student's t-distribution is a little bit more suitable if we don't know the population variance as well. In other words, we don't know what the variance would be. When testing for zero difference between the groups, use the following simplified test statistics. If there is no difference between mu1 and mu2, then mu1 minus mu2 equals 0, right? So therefore, that part of the equation can be removed. We don't need to include that. So in most cases, especially when using R, these are the calculations that are being used. Case 1, case 2, or case 3. In most situations, I would almost always recommend to use case 3 unless you have some special information about your population, which is very rare. All right, so how do we test two means? First, same as with the one sample hypothesis, step 1 is state the hypotheses. Step 2, specify the decision rule. Choose the level of alpha. Again, usually alpha is just 5% in most social science applications. Step 3, calculate the test statistic or test statistics. Step 4, make the decision to reject the null hypothesis if the test statistic falls in the rejection region or regions in a two-tailed test as defined by the critical values. Then take action based on the decision. Very similar, almost the same steps, but the actual testing procedures are a little bit different when we have two samples. So which assumption is best? If the sample sizes are equal, the case 2 and case 3 test statistics will be the same. Although the degrees of freedom are a little bit different, the results will be the same if the sample sizes are equal. If the variances are similar, the two tests will usually agree. You usually get the same result between case 2 and case 3 if the variance is similar. If there's no information about the population variance, then it's best to choose case 3. There's less assumptions in case 3. However, given the same data, it's a little bit more difficult to get a significant result in case 3 because we have less certainty about the data underlying it. Note that unequal sample sizes are common and the formulas are still applicable. You can use different size samples because the equations accommodate for the size of each sample. So the central limit theorem, CLT, states that the distribution of sample means approximates a normal distribution as the sample size gets larger, regardless of the population's distribution. Usually, we consider 30 above 30 as following a normal distribution. Sample sizes equal to or greater than 30 are often considered sufficient for the CLT to hold. A key aspect of the central limit theorem is that the average of the sample means and standard deviations will equal the population mean and standard deviation. A sufficiently large sample size can predict the characteristics of a population more accurately. Obviously, if you have a bigger sample size, it is more accurate to predicting or estimating the population parameters. For a large sample size, for unknown variances, if both samples are large, your sample 1 and sample 2 are both more than 30, and the population is not badly skewed, you can use the following formula. Now, be careful of these three things. Are the populations skewed? Are there outliers in your data? You can use histograms or box plots to check if you have some outliers or a heavy skewness in your sample. Check if your sample sizes are large or not. If your sample sizes are very small, the mean is not very reliable and it may lack statistical power. Is the difference important as well as significant? In other words, sometimes you may find that there's a significant difference between the groups, even if that difference is really, really small. Especially if we have really large sample sizes and we're testing two very large samples, in many cases, we might find a statistical significance, meaning the two groups are different, even if that difference is very, very small. So ask yourself, is it important if that really small difference is existing, or does it not matter? So statistical significance doesn't mean that your result is important. All right, comparing two means in a paired sample. Sometimes data occurs in matched pairs. This happens when the same item is observed twice, but under two different circumstances. Paired data can usually come from a before and after experiment. For example, blood pressure is taken before taking a treatment and after taking a treatment. In that case, we have paired samples. What does that mean? It means that observation 1, we have a sample 1, someone is taking their blood before getting treatment. Then sample 2 is that same person getting blood after the treatment. The second observation is simply a different person, and sample 1 would be a before, sample 2 would be an after. This helps to alleviate any variation between each individual observation. So paired samples eliminate a lot of the uncertainty due to different individuals in your samples. So if you have paired samples, then we have a different test we can use called a paired t-test, which is a little bit different than the previous examples. The mean and standard deviation for the differences D are given below. Because the population variance of D is unknown, we will do a paired t-test using students T with n-1 degrees of freedom to compare the sample mean difference, D bar, with the hypothesized difference, mu difference. Usually, mu difference equals 0. The test statistic is really equivalent to a one sample t-test. So when using paired samples, step 1 is to state the hypotheses. Here's an example, mu D, the difference is 0. The alternative hypothesis is that there is a difference between the two samples. Specify the decision rule. Choose alpha. Again, generally this is 5% or sometimes 1% or sometimes 0.1%, but usually about 5%. Calculate the test statistic T, make a decision based on that test statistic, and reject H0, the null hypothesis, if the test statistic falls in the rejection region. In the previous video, we looked at one sample hypothesis tests, but we haven't looked at how to solve those using R. Now we've also learned two sample hypothesis tests, and now let's look at how to solve both of these types of hypothesis tests using R programming. Okay, so let's look at our first problem. The mean arrival rate of flights at Gimpo Airport in marginal weather, when the weather's not that good, is 195 flights per hour with a historical standard deviation of 13 flights. In other words, Gimpo Airport probably looked, this is not a real example. Gimpo Airport could look at their records and calculate that there's maybe 195 flights per hour on average and a deviation of 13 flights per hour. To increase arrivals, a new air traffic control procedure is implemented. In the next 30 days of bad weather, the mean arrival rate is 200 flights per hour. Set up a right-tailed decision rule with a strict decision rule. So what we have is, historically, they've had 195 flights per hour. After implementing a new air traffic control procedure, now they have about 200 flights per hour. So we want to know, is this a significant change? Has it increased? Because we're looking at one direction, specifically, did the flights increase significantly? We can look at only a right-tailed decision rule because we are only interested in that side of the distribution. Okay, with a strict decision rule, what does a strict decision rule mean? Well, I'm not sure exactly based on this problem. 5% is not very strict. It's pretty standard. So maybe a strict decision rule might be 1% or 0.1% set of alpha. Let's switch to R. How do we define the hypothesis test? Well, it's kind of described for us already. It's a right-tailed hypothesis test. Is it a one-tailed test or a two-tailed test? Let's check the data that we have, and that might give us some more information about what is the best method to use here. Okay, so in this file, I'm going to load the library OpenXLSX. If you haven't installed OpenXLSX, then you should first install the package onto your computer. If it's already on your computer, we can skip that step and simply load the library into R. OpenXLSX allows us to open Excel files into R directly. So because my code file, this script file, and the data file are in the same folder, I don't need to change my working directory. So I'm going to skip this step as well. If your script file for R and your data file for the practice exercises are in different locations, then you should probably fill in the location of where that Excel file is located on your computer here. Because I don't need to do that, I'm going to skip that step. So as long as we have defined the right location, let's just load our data. Here I'm loading 5 different data sets from the same Excel worksheet, but each worksheet is on a different sheet, so I'm saving those under different object names here. Okay, so the first thing I would like to do is to check that data. So first we're going to be dealing with this flights data, so I'm just going to hit enter here, and this is what that flight data looks like. Number of flights, and presumably this is each hour. So 1 hour, 2 hour, 3 hour. They had about 210 during 1 hour, 215. So this is the data that we have. How many samples do we have? We only have one sample here. So just by looking at the data, we know that we have to use a one sample hypothesis test. Let's look back at this problem. So we have 195 flights per hour historically. This seems like a good assumption that the null hypothesis is Gimpo has 195 flights per hour. Okay, so how do we do a hypothesis test? If our data set is small, if the sample size is very small, then we should use a t-test. If our sample size is very big, well, a t-test approximates a normal distribution if our sample size is very big. So we can just continue to use a t-test no matter what size data we have, because the t-test accommodates for the size of the sample. So let's explore this t-test function. If we use the question mark, and the name of the function is t.test, let's run this code here, and it will bring up our help menu. Let's make it a little bigger. T-test is in the stats package. That means that it's included with R by default. So we can perform a 1 or 2 sample t-test on vectors of data. In other words, we can use the same function for a 1 sample test or a 2 sample test. So let's read a little bit more. Looks like this: x, y equals null. That means that we don't need to use y. We have an argument called alternative. One, we could choose a 2-sided test, a less test, meaning a left-tailed test, a greater test, meaning a right-tailed test. We can change mu, particularly, mu is going to be our mu0 if we have a 1-tailed test. If we have a 2-sample test, meaning we have 2 vectors, 1 vector of x, 1 vector for y, we have 2 samples of data, then mu refers to the difference. If you remember that difference value, that's what this mu represents if we're using a 2-sample test. In most cases, that would just be 0. If we have a paired t-test, then we can change this paired argument to true instead of false. By default, these are all of the values that are run by default. The confidence level is 95%. In other words, by default, alpha equals 5%. I've included my explanation of what these do here. I'm going to skip down to question A. A1, where we have to define our test, it's a 1-sample test. Why? Because we only have 1 sample of data. It's a right-tailed test because we're testing if we have more than our predicted mean. And what is our assumed mean? What is mu0? Mu0 is that historic number of flights, 195 flights. Next, we should define our decision rule. I'm going to define our decision rule as 5%. So if you wanted to make it a little bit more strict, you could use 1%. I'm going to use 5%. It's not that strict. So now we're going to use our function, the t-test function. All right, so we're using our t-test function to check our data. Our data is flight data. It looks like this, number of flights, and each value is the number of flights per hour. Alternative, greater, means that we're doing a right-tailed test. We're only interested if our test statistic is significantly greater than our predicted mean. What is our predicted mean? What is mu0? Mu0 is 195. Finally, our confidence level is the same as 1 minus alpha. In other words, 95%. All right, so what are the results of this test? So I've copy and pasted the results here. Let's run our code and look at the results in real time. Let's clear our console. Let's run our test. All right, so let me make the console larger so we can look at the results. So here are the results of our test. So how do we interpret these results? It tells us that it's a 1-sample t-test. So that tells us whether we did the right thing or not. We can check, okay, I wanted to do a 1-sample t-test, so that's good. The data, it's telling me I used this data. It gives me a t-statistic. It tells me how many degrees of freedom I have, and it gives me a p-value. To use the p-value approach, we can just check if this p-value is less than the alpha value that we want, then we would reject the null hypothesis. I input that information already. So the alternative hypothesis is the true mean is greater than 195. So R already knows what our alternative hypothesis is because we used a right-tailed test. So is our test significant? Let's look at our p-value. Our p-value is 0.02. Is this less than 5%? Yes. That means the probability of having this sample and getting this result is less than 5% by occurring randomly. In other words, if it's so rare to occur to have this sample statistic, then we could probably safely assume that it's not due to chance because the chance of getting this result is less than 3%. It's about 2.3%, right? So in that case, because we set alpha to 5%, then this p-value is significant. What does that mean? That means we should reject the null hypothesis and look at our alternative hypothesis. The true mean is greater than 195. So what is our decision? What decision should we make? We rejected the null hypothesis. So what decision should we make? It seems like the new air traffic control procedure was successful if they wanted more flights per hour. So maybe what should we do? Maybe we could give the person who thought of this new procedure a raise or a promotion or something like that. Or maybe we could tell another airport to use the same procedure, for example. Okay? All right, so let's check our next example. Beer shelf life is a problem for brewers. They want beer to stay on the shelf for a long time, but they want it to stay fresh for a long time. When beer is stored at room temperature, its flavor gets worse. When the average furfural ether, I'm not sure what that is, content reaches 6 milligrams per liter, a typical consumer begins to taste an unpleasant chemical flavor. In other words, if this specific chemical reaches 6 milligrams or more, the beer tastes bad. Check if a random sample of beers that have been on the shelf for more than a month have exceeded the 6 milligram threshold. So what is our hypothesis? What is our decision rule? How would we analyze this? Okay, so question B, we're looking at a one sample test, a right-tailed test, and our mu0 is 6 milligrams. In other words, we want to know, do we have more than 6 milligrams in our beer? If so, that would be a problem. So let's look at our data. Our data is called beer. Let's check what that looks like. Here we go. Here's our data. Let's look at the console. We have only 12 beers that we're checking. And each beer is listed the milligrams per liter, but we have a very small sample, right? So, of course, we should use our t-test. Okay, so how do we use our t-test with this data? Well, we should use our t-test function, t-test. And what is our data? Our data is called beer. And what kind of test do we want to do? We want a right-tailed test. We actually previously did a right-tailed test right here. We used alternative equals greater. So I'm just going to copy and paste that into our code. All right. So our t-test beer, let's just organize that a little better. Here's our data. Here's the type of test that we're going to do. Next, our mu equals 6 milligrams. Again, we did this before. Using this code here, mu 95, 195. Just going to paste that here. And actually, this is all we need to do. We need to change our mu to 6 milligrams. We're concerned if we have more than 6 milligrams. Let's just run our code here. Actually, if we're using alpha equals 5%, we actually don't need to input that alpha directly into the t-test function because it assumes that our confidence interval is 95. And we use that alpha just to check if the p-value is less than that value. So I can just check my p-value. Is it less than 5%? Yes. So what should we do? We should reject our null hypothesis. Okay, so if we see our degree of freedom is 11, why? Our sample size was 12, 12 minus 1, our degrees of freedom is 11. Our p-value is very small, it's less than 5%, so we should reject our null hypothesis. So what does that mean? It means the true mean is greater than 6. All right, so what does that mean? That means our beer is going bad. What should we recommend to this brewery or this pub or this bar? We should tell them to throw out that beer and get fresher beer, right? Or maybe use preservatives in the beer or something else, right? We need some domain knowledge to really recommend something intelligent. We really need to understand the business environment or the environment of the decision that we're going to make a really meaningful recommendation here, okay? But in R, we can do all of that just using this function here. All right, you can see the next example here. Let's check the next example. Wine. pH is a measure of acidity that winemakers must watch. A healthy wine should have a pH between 3.1 and 3.7. However, the winery is worried that the wines are too acidic this year. Acid has a low pH, so they're worried that maybe the level is too low. Therefore, use the data to do the following, to find the hypothesis test. Okay, so we should think about this a little bit. They're worried that the pH level is too low. Usually, the pH should be between 3.1 and 3.7. So what are they worried? They're probably worried the pH level is below 3.1, because if it's above 3.1, as it says, it's a normal range, it's a healthy wine. If it's below 3.1, it might be a problem. So what kind of test do we have? We probably have another one sample test. Why? Because what we're worried about is that our sample is below a benchmark, that benchmark being 3.1 pH level. So let's look at our R code again. Okay, so question C, we have a one sample test and we're looking at a left-tailed test because we're worried the pH level is going too low. So let's copy and paste our previous example and we can just change our data as we see. So wine is our new data. We're not looking at greater, we're looking at less. And our mean is 3.1. This is the benchmark. This is our mu0 that we're worried the wine might go below. So using our data, I'm just going to check our data, run. This is what our data looks like. We have 16 bottles of wine, and we have the pH levels of all of those bottles right here. Let's check if that pH level has gone below 3.1. Let's look at our results. We have a one sample t-test, good. We have a degree of freedom 15. Our p-value is 1. What does that mean? Our p-value is 1. Well, is that less than 5%? No. So should we reject the null hypothesis? No, it means we failed to reject our null hypothesis. What was our null hypothesis? The null hypothesis was our pH level is 3.1 or higher. So we don't care if it's higher, we're only concerned if it's less. In that case, our wine is not too acidic, so we can tell the winery they can sell their wine as normal. Let's look at question D. This one is a little bit more complicated. At alpha level 5%, does the following sample show that daughters are taller than their mothers? Is the decision close? Let's look at our data. So in question D, we're trying to check, are the daughters taller than their mothers? All right, so what kind of a test do we have? We probably have a two sample test. So let's check the data. Our data is called family height. So if I check that data, I see that I have family ID. So this says this daughter height and this mother height are in the same family. this daughter height and this mother height are in the same family. So what kind of a test should we use here? We should use a paired t-test. Why? Because this family is related. This daughter and mother are related, so they're paired. This mother and daughter are related, so they're paired. So how do we do a paired t-test in R? Well, you might have guessed we also use t-test function. Now you're getting it. Okay, so because we have a paired two-sample test, I need to indicate my testing data for my X and my Y groups. I have two samples, so I need to indicate my first sample, daughter height, and my second sample, mother height. How do I access the daughter height from my data set? This is a data frame. To get that one column, I can write $, meaning give me just one vector. Daughter height is the name of that column. So if I run this code, it gives me just those daughter heights here. If you can see, 173 is the last value, 181 was the previous value. All right, so there's my X sample. There's my first sample. My second sample is family height from the same data set, but this time I want the mother height. Let's check that. There are my two values. All right, so how do we test these two samples? All we have to do is use our t-test. And let's put the daughter height first, comma, our second argument. Align that a little better. So here we have our first sample, our second sample. Next, what do we need to do? We need to say we want a right-tailed test. How do we do that? We use the alternative equals. We're looking at the right tail, which is greater. So we would write greater, comma. We're missing one argument, which is what type of test is it? It's a paired t-test. So we need to change paired to true. And those are all the arguments we need to deal with here. Let's clear our console and run our code. So here is our result. Are daughters taller than their mothers? In this data, well, we see our p-value is 0.0509. Is this less than 5%? Technically, no, it's not less than 5%. It's marginally significant, meaning at the 10% alpha level, it would be significant, but technically it didn't end up in that rejection zone, which would be any p-value less than 5%. So in this case, we don't have enough evidence to reject our null hypothesis. So what could we recommend to the researchers? Well, we have a very small sample. We have a very small sample size, and it's almost significant. I would recommend to get a new sample and test again. It's very close to significance. I would probably recommend to get a larger sample so that they have a more I would recommend that they probably get a larger sample so that they can get a more powerful test. All right, let's look at one more example here. Here is our last example, coffee temperature. Coffee has been tested among 2 Starbucks coffee shops over the course of several months. Check if there's a significant difference between the temperatures of the coffee in the 2 shops. In other words, as you usually see with Starbucks, they might be right across the street, and you want to test is the consistency of coffee temperature similar between the 2? Or is there a difference between the coffee temperature, right? So let's check. What kind of test do we have here? In this case, we don't care which one is greater or less than the other, so we should probably use a two-tailed test. It doesn't matter which group is higher or lower. We also probably want to use a 2-sample test because we have 2 samples. One sample from one Starbucks and another sample from a different Starbucks coffee shop location. Okay, so let's go back to R and see what we can do. Okay, so in this example, our coffee data is called coffee temperature. So let's check. Here is our samples. We have two equal sample sizes. All right, so we have coffee shop A, coffee shop B. So is this a paired test? We have coffee shop A and coffee shop B. What does it mean to have a paired test? A paired test means each row of data is related. Is this person's coffee related to this person's coffee? No, they're totally different people. So we can't use a paired test here because there's no relationship to the index number 1 or 2. They're just two different sets of random samples. So because the order is not important, we can't use a paired test here because each row is not related to each other from one coffee shop to the other. Okay. All right, so what should we do with this data? Let's test it using our t-test. So again, we have two groups. So here we have our coffee shop A. So I'm going to say, from our data set coffee temperature, give me coffee shop A temperature. That is our first group. Our second group, our second sample, looks like this, and that would be coffee shop B. So now let's again use our t-test. All right, so here's my first sample. Here's my second sample. I just like to align it. It's a little bit easier to read. All right, do we need to do anything else in this t-test? What is our alternative? Well, in this case, our alternative equals a two-sided test. All right, do we have a mu? Well, the mu value in a two-sample test indicates the difference. Well, I'm assuming that there's no difference between these two groups, so we don't have to write anything else. We don't have to define the mu here. Is it a paired test? No, so we also don't need to define the paired argument because by default, the paired argument is false and the mu argument is 0. And that's what we want. All right, so do we have to do anything else? I think we can run our code. Let's clear our console and run our code. All right, so what do we have? Let's check. All right, so this is a Welch two-sample t-test. We'll come back to that in a minute. So let's check our results. Our results say our p-value is very small. That tells us that one coffee shop is different than the other coffee shop. In fact, if you look down here, it tells us the mean of x is 170 and the mean of y is 161. Now, I don't know what the best temperature for coffee is, but I would assume that a hotter coffee might mean that it's more fresh, or that it took less time to give to the customer, or that it's been boiled better. Now, I might be wrong, but my guess would be that there's a problem if it's cooler rather than hotter. All right, so what would I recommend to this coffee shop? I would recommend that the coffee shop look into whichever coffee shop location is location B, and figure out why their coffee is not hot enough. Okay, maybe there's a quality control problem, maybe a manager is doing something wrong. So I would ask the manager to do a little bit more research as to why there's a difference, but based on this data, we can say there is a statistically significant difference between the two groups. Now, let's go back to this. What does it mean a Welch two-sample t-test? If you remember from the slides earlier, there are several different cases, case 1, case 2, and case 3. And I said we should almost always use case 3. So let's check this. We can check our t-test function and get some information here. We see that it is paired is false. Equal variance is false. Okay, so actually, if we look back at our presentation file, we see that the case 3, which I said we should almost always be using, is the Welch-Satterthwaite test. And if we check this R code, it tells us that that is exactly the test that we're using. We're using that case 3 by default. If you wanted to change that case 3 to a case 2, for instance, you could change var equal to true, and that would be case 2. However, there are very few times that you would probably want to use case 2. I would say stick to case 3 in almost every situation. Now, what about case 1? Case 1 is actually not using a t-test. Case 1 is using a normal distribution or a z-score in a normal distribution. So this t-test function is very useful for case 2 and especially case 3. So I urge you to almost always use case 3 unless some very rare circumstance where you might know something about your population. All right? All right, cool. So I hope this R tutorial was a little bit helpful. I find it a lot more useful to look at real examples rather than just the theory of how the hypothesis test works. This is much more practical, and understanding what to do with the information after you test it is also a skill that's worth spending time learning. All right, so thank you for listening to this lecture. This lesson was about hypothesis testing. This concludes our lessons on 1 and 2 sample hypothesis testing. I hope the examples in R are more practical and useful for you in your own research, rather than just studying the theory. While the theory is important, understanding how to use it is much more important. So I urge you to go through these examples, maybe look at some other examples on your own if you have to use hypothesis testing in your own work. Thanks again for listening. This is the Applied Statistics Using Programming lecture series. I'm Dr. Ian from Sogang University. Thank you for listening, and I hope to see you in the next video. Thank you. The digits. So let's clear our console and run our test. Oops, I forgot a comma. Let's clear our console and run our test. What am I doing? All right, so let's run our test. What? Oh, shoot, I'm so stupid.